Thank you for the warm welcome. So before I start talking about galaxies, which is something I've been researching for more than 10 years, as Charles mentioned, I want to just emphasize that I'm really excited to be here on the coast, but not just because it's the Sunshine Coast. For me, a big reason why I'm doing astronomy professionally now is also because when I was a teenager, I went to outreach talks like this and I got inspired. So I try to give back when I can, and I really appreciate opportunities like this. So thank you for having me. So yeah, I'm going to tell you about galaxies and take you through a journey through cosmic time. And here are some of my favorite telescopes that are in space. You would recognize the James Webb Space Telescope with its iconic shape of the mirror. And there's also Euclid, which I will talk a little bit about. It's a new telescope that was launched last year on Canada Day. And then the Hubble Space Telescope, which, as you know, has been in operation for decades now and has supported a lot of the research that I have done so far. So I mentioned Hubble. I did my PhD thesis on Hubble because, well, Hubble was launched in the 90s. And then since it's been launched, it's been taking very deep images from space of the deep sky. And I thought it really revolutionized the field of galaxy evolution. This is one of the deepest images that the Hubble Space Telescope has ever taken. Almost every blob that you see here is a galaxy, like our own Milky Way. And you see they have different shapes and colors and sizes. So really, I mean, people knew that galaxies existed, you know, since Edwin Hubble presented the Hubble tuning fork in 1920. But I think Hubble really gave us a sharp view as we can see through our optical eyes, what galaxies truly look like. And it's fascinating. And there's a lot of interesting questions that we have not yet been able to answer. So fast forward to the James Webb Space Telescope, which you know, have been in operation for more than 2 years now. This is one of the images that have been taken of a galaxy cluster called the El Gordo. And if you understand a bit of Spanish, El Gordo means the big one. And here in this context, it means it's a very heavy galaxy cluster. A galaxy cluster is basically a cluster of galaxies that is bound together in a giant dark matter halo. So we don't see dark matter directly because, as the name suggests, dark matter itself does not emit light. But what we see in optical and infrared light, as seen by the James Webb Space Telescope, are individual galaxies. And many of these galaxies, they are actually gravitationally bound together in this bigger structure called a galaxy cluster. And I'll come back to galaxy clusters later. But what I want to show you is also that behind galaxy clusters, you may see these long streaks of light. That is an effect called gravitational lensing. And that is something that Einstein predicted. And now we are actually able to see. So these are actually background galaxies behind the galaxy cluster whose light has been bent, very much like when you look through a wine glass, you see a background light being bent into shapes. So this kind of distortions, we can study that and use that to trace the distribution of dark matter in the galaxy cluster. So this is also something that I'm very interested to study. You see streaks and you also see, you know, U shapes bent around a foreground galaxy like that. So just to bring everybody to the same page, what is a galaxy made of? We know we are in the galaxy called the Milky Way, but what is it really? Here, I think there's a nice illustration that that shows the true scale of what we are dealing with. So we are zooming in on M87 or Virgo A by scale of 100 million, right? So you start from the night sky, you look for the constellation, and then as you zoom in more and more, you're starting to see clusters of galaxy, and this is M87. And when you zoom in, you're starting to see starlight, but then there's also gas around it. So it is surrounded by hot 1 million Celsius gas. And then you see this jet that emanates from the very center, from the heart of M87, right? So when you go to the very center, we see, well, this is actually a video made by the Event Horizon Telescope. This is one of the few pictures ever taken of the event horizon around a supermassive black hole. And this one is the one sitting at the heart of M87. And by now, we think that most massive galaxies at their centers, they host supermassive black holes. And this is important because, as you see, even though the black holes are tiny, they can influence matter on much bigger scale. So in order to better visualize the scales that we're dealing with, let's have this static picture of a galaxy. And I will introduce a new length unit called the parsec that some of you may have heard of, but a parsec is simply an astronomer's way to define a length scale. So a parsec is roughly 3 light years. So it is quite big, it is handy. When we describe a galaxy's size is roughly 1,000 parsec or 1 kiloparsec. And when you zoom in to each of these brighter blobs in here, you have star-forming regions like Orion, for example. It is an example of star-forming region where you have young stars that are born in clouds of gas and dust of very cold temperatures of a few tens of Kelvin or minus 200 Celsius. And then I talked about in the hearts of galaxies, you have supermassive black holes. So when you zoom in to the very center, so we can't actually see the black holes themselves because these are very challenging imaging observations that the Event Horizon Telescope did. So this is just an artist's illustration of what it looks like around a supermassive black hole. So around a supermassive black hole, well, at the very center within the event horizon, there's no light coming out, so it's a dot. And then around it, there's an accretion disk, which is matter that is being spiraled in to feed the black hole. And because of the extreme conditions of this accretion disk, actually this accretion disk is super hot, and you can think of it as a disk where matter, so gas, are on very chaotic orbits, and gas is being heated to millions of degrees Celsius because of this energetic event. And another way to help the black hole to feed is that periodically there could be relativistic jets of plasma that is being sent out in the polar direction in order for the gas to get rid of the angular momentum so that gas could better fuel the central black hole. And a side effect of that is that you see jets, which is what I showed you in the previous animation. And then coming back to even bigger scale, so galaxies do not always live in isolation. So when you zoom out 1,000 times on megaparsec scales, galaxies could reside in different environments. Some of the most extremely dense environment is a galaxy cluster, as you saw for El Gordo. Sometimes galaxies could live in smaller groups of a few galaxies, and they are bound together gravitationally. And sometimes you can find galaxies in voids where they are in isolation from each other. So I think of it as like humans, right? You could be living in Vancouver, or you could be living on the coast, or you could be living in the suburbs or even rural areas where you're in the forest and there's no one. So galaxies are a bit like that too. And this is also a research area that I'm very interested in. And I have students that work on, what difference does it make if a galaxy grows up in a void versus in a group versus in a galaxy cluster? And I'll get to that in just a bit. So we are all familiar with the Milky Way, but if we are able to transport ourselves out of the Milky Way, which will never happen in my lifetime, and even this is what it should look like. So this is the top on view, and this is the edge on view. So the sun is roughly 8 kiloparsec from the center. In the center of the Milky Way, there's a bulge. There's a supermassive black hole that is not an active one. We don't have strong jets that is currently being emitted. And then there's spiral arms. So the sun is on one of the spiral arms. And some of the structure is more obvious when you look at it edge on. You have the galactic disk. So it's a plane of disk of stars on a disk, and the sun is part of this galactic disk. And then you have the bulge, which is made of overall older stars, which is why it looks, a bit more orange compared to these stars, which are younger. And then outside of the disk and the bulge, you have the stellar halo. So there is a small fraction of stars that is living on this halo. They are more on random orbits, and they trace the dark matter halo. So they're still gravitationally bound to the Milky Way, but then they are on random orbits whereas stars that are on the disk, they are on orderly rotation orbits. And then within the halo, you also have globular clusters, and I'm sure you can see some of those globular clusters from a telescope. And all of these different components within the Milky Way, they have different properties in terms of the age of the stars, the orbits of the stars, and also the metallicity, so how chemically enriched the stars are. And those are things we can study when we get spectra, and we can use those pieces to help us infer the formation history of the Milky Way. So in terms of the absolute mass composition of the Milky Way, actually the stuff that we know and we are made of and that we're familiar with only makes up a tiny fraction. So I would count us as being planets, and actually that is the smallest component of the Milky Way. That's the yellow one. And then the Milky Way is also made of dust and gas, which is what you can see, from which young stars are born around the Orion Nebula. And then you have the supermassive black hole, which is also pretty heavy. And then you have stars, which are the starlight that we see at night, and including the sun as well. And then actually most of the matter is not luminous. They are called dark matter. And we know they're there from different lines of evidences to see how galaxies rotate. We know that there's more matter than we can see in the starlight. But I think, yeah, that is another active research area to understand the true nature of dark matter, whether they are black holes that don't emit light, or they're smaller particles like neutrinos, for example. So what you have already seen before in the Hubble and JWST images is that galaxies have very diverse shapes. So our Milky Way has a disk, has the bulge. But when we look at external galaxies, I mean, there are billions of galaxies out there, and we're just one of those, our Milky Way. You can notice differences. You have galaxies that are bluer, some that have smaller bulges, some that have larger bulges, some that have more developed spiral arms, some have fewer spiral arms. And then when you look at the ellipticals, some have dust lanes, for example. This one has dust lane, and some don't have dust lanes, right? So really the goal of our research area is to understand how galaxies take on these different shapes and colors, and what is the physics or processes that are driving the evolution over time. So this is another depiction of what it means to look at galaxies, because in astronomy, as you know, well, that's the speed of light is a constant, right? So that means that the light that we see of galaxies actually could have been emitted like billions of light years ago, and it took that much time for the light to reach our eyes and to reach our telescope. So in fact, the light that we're seeing, it came from a long time ago. So you can say that we are studying the history of the universe this way, and it's always very fascinating. So we can measure distances, or what we call redshift, to galaxies from observations, and therefore we can infer, how long ago was this light emitted. So this is what nearby or present day galaxies look like. This is what galaxies used to look like when the light was emitted 4 billion years ago, and here 11 billion years ago. So you see some similarities in structures where, galaxies that have spiral arms, they already existed 11 billion years ago. And similarly for, galaxies with bulges, we also found them, when the universe was only a few billion years old. So whatever mechanisms that cause the formation of spiral arms or ellipticals, they must have already been in place, and the conditions must have been right even early on in the universe history. And for context, 11 billion years, that is looking like 3/4 of the universe history. So that is quite significant amount of time. So I want to highlight citizen science project that you may have heard of, but if not, I find it's pretty cool. It is a project called Galaxy Zoo. It is made like a game, but we actually do science with it. So it is a website where people can just log on and you can classify galaxies. By now, I would have told you enough, and you will be able to do this as well. Basically, you're given a bunch of images, and then you're asked some questions to help sort galaxies shape. So for example, is it smooth? Do you see features like spiral arms? Do you see a star or artifacts? And the reason for doing that is that even though we use a lot of computer programs and develop them in order to help us classify shapes of things, we find that the human eye is still quite useful and sometimes more robust than computer programs that we develop in order to quantify shapes. And in fact, this Galaxy Zoo project had been launched for some years now, and those human classification have helped scientists to train better computer programs in order to have better classification, because right now we have galaxy catalogs and images of billions of galaxies, right? It is not possible to have humans to look through all of them. So what we do is that we take this as a training set in order to develop algorithms that we apply on all the galaxy images. And so this is a result of different research papers. There have been more than 60 research articles that make use of the result of Galaxy Zoo classifications. So these are some ways where I think people can really contribute to doing science, to advancing science. You don't need to go to university to do that. You just need to be interested. You just need a computer in order to do that. And I find it fascinating. So Galaxy Zoo is one example. And I'm aware that there are other citizen science projects, for example, for classifying gravitational wave signals and other sorts of science. And I think we are still working on different, basically untapping the excitement and interest of the public to help us do better research. So I want to speak a bit about spectroscopy. I talked about it as a way to measure accurate distances and redshift to distant galaxies. Spectroscopy is another tool that we use in order to perform very precise measurements of distant objects. So the thing about doing astronomy is that it's not like we have a lab where we can take samples and then we analyze them, right? The only thing we can do is to look through our telescope. So in order for us to get more information, what we do is that we build better and better instruments in order to find better and smarter ways to get the information of these distant objects that we never get to. So spectroscopy is one of our tools. So a way to understand what spectroscopy is that we can understand rainbows, right? It's like if you have a prism or you have a prism, you can disperse light, for example, light from the sun or light from a light bulb and any light source really, disperse it into what we call different wavelengths. So you can see the rainbow. And what happens when you have an intervening gas cloud between this light source and this light source here, in our case, would be a distant galaxy. When you have an intervening gas cloud, depending on the chemical composition of this cloud, actually it will leave some fingerprints. So there would be certain transitions that correspond to the chemical composition. Let's say hydrogen. If this gas cloud is made of only hydrogen, we will see spectral lines that correspond to hydrogen here. And if we don't have this continuum light source, and if you only have a hot gas cloud, then this gas cloud could be emitting the same line at the same wavelengths. So this is a method that we call spectroscopy. And here is a beautiful spectrum of our sun. This is represented in optical or visible light, starting from blue and purple all the way to red. And you see the sun has so many spectral lines, and this reflects the chemical composition of the sun. And in fact, the chemical composition of the sun is not too different from the chemical composition of, for example, asteroids or things that you find in the solar system, because in the end, we are born from the same kind of gas cloud that then collapse to form different structure. So things that you eat as minerals, you can also find them in the sun. So here is another representation of what we do in spectroscopy. For example, these are different elements like sodium, nitrogen, hydrogen, oxygen. And so on the horizontal axis, you have the different transitions or wavelengths. So the positions of these transitions can be worked out from quantum mechanics. And what I'm trying to convey here is that each element has a unique chemical fingerprint. So conversely, we can make use of this fact to say that, okay, if I'm looking at the distant galaxy, I see spectral lines here and here. You can do some cross-matching in order to infer the chemical composition of this distant galaxy that we are looking at. And the other thing is that if you want to measure distances, these spectral lines get shifted towards the red because of the expansion of the universe. If the galaxies emitted light 10 billion years ago, by the time this light reaches us, the universe would have expanded. So that helped to stretch the photons or the light packets. And so by looking at these spectral lines, we can also infer distances very precisely to these galaxies. And by the study of spectroscopy, we have been able to infer the origin of the elements found in the solar system. So this is the periodic table that you might have seen. The most common elements in the universe is hydrogen and helium. And then there are elements that we are made of, primarily carbon, oxygen, and then the things that we maybe take in our diet, like iron, zinc, and so on. So actually, we now have explanations for where each of these elements come from. In the Big Bang, it was only the simplest elements that were created. So hydrogen, helium, a bit of lithium, and then the remaining elements are all created in stars of different kinds. They could be created in merging neutron stars and low mass stars. They create the heaviest elements. And then you have the intermediate elements that are created in massive stars and white dwarfs. So I think it's still very fascinating to think about, whatever that makes up our body, they come from previous generations of stars. And in fact, how we are made up of, it's not too different from the solar system as a whole. I think it's fascinating. So coming back to galaxies, I want to show you what typical spectra of the two different kinds of galaxies look like. This is a typical elliptical galaxy, and this is a typical spiral galaxy. So this is what a spectrum looks like. On the vertical axis, that is the brightness. And then on the horizontal axis, that is the wavelength. So here we are looking at an optical spectrum. So this is more like what human eye would see as purple light, all the way to red, and then infrared. So do you notice differences between the spectra? What differences do you notice? Any guesses?
One's a flat line.
Yeah.
No, one isn't. One isn't. One.
Right. Yeah.
Yeah.
What about?
Right on a massive, particular space.
Yeah, those are very good observations. So we have explanations for all of this, but you're right. I think one main difference here is that you see a lot more emission lines here. You have the spikes, and then in elliptical galaxies, you have the complete absence of emission lines, and you only see absorption lines. So the brightest line here in the optical is H alpha, so that is ionized hydrogen. You would also be familiar with it because we use it in astronomy to look at the sun, for example. And in fact, ionized hydrogen is a main tracer for star formation in external galaxies, which makes sense because, you look at the sun, you see H alpha. And in fact, when we look at external galaxies, the more H alpha you see, the more stars the galaxy is making. So it is a tracer for star formation rate of galaxies. And then the H alpha is usually bracketed by ionized nitrogen, which can be a tracer for chemical enrichment, but also an active galactic nuclei. So there's a lot of interesting physics that go into all of this. But the fact that elliptical galaxies have an absence of emission line shows us that it does not have strong star formation. This is where H alpha is, and you don't see it emitting. And that suggests an absence of young stars. And it is correct because this shape here, it is what we call in physics black body emission. And this is quite typical. And you can use the shape of this kind of bump here to infer the temperature of this black body. And that tells us that an elliptical galaxy is indeed made up of quite old stars that are billions of years old. So it's not very active compared to spiral galaxies, which are a lot more active. So really, I could give another lecture on this, and I don't have time to, but what I'm trying to say is that there's a lot of very interesting information that we can infer from spectra, from what kind of lines are present, how broad they are. Sometimes that suggests the presence of an active supermassive black hole, and you have heavy elements like magnesium, right? And the ratios between magnesium and simpler elements like hydrogen tells us something about the star formation rate timescale of galaxies. So we use these things to infer the history of galaxies. And I think spectroscopy is wonderful for this reason. So if I have to summarize my work, I think this is how I would do it. We collect data, and for us, data means getting images and spectra of a lot of galaxies. And then we measure information like, what is the color, what is the shape of a galaxy, and what is the line width, or what are the elements present. And then we use our knowledge coming from physics in order to understand, okay, what does this mean about the condition of a galaxy? Does it mean it's old? Is it young? And how many stars is it making? And then we try to, in doing science, we try to come up with hypotheses that can explain properties of galaxies as a whole. And those hypotheses allow us to ask new questions to test our hypotheses. And hopefully one day we get to wisdom where we actually learn more about galaxies and how they evolve over time. But effectively, because galaxies evolve so slowly, their evolution timescale is billions of years, and that is much longer than our lifetime, right? So effectively, when we look at galaxies, we are looking at the snapshots, different snapshots of different galaxies at different points of their lives. So we can't really wait long enough to see how they actually evolve in real time. And I think that is where it differs from astronomers who study, for example, supernovae explosion. You wait for a few days or a few years and you see a difference. Here, when we study galaxies, no, we don't see any difference. So we have to use our imagination and our knowledge of physics in order to better understand them. So here is a result of one of these approach. So here, what you're looking at is what we call a cosmological simulation of certain volume. So we are looking at a very zoom out view. Each of these blocks that you see is a simulated galaxy, and we are playing this movie forward in time. And so what you see is that galaxies, so this is on tens of mega parsec scale. What you see is that galaxies, they build and become bigger by merging with each other. So galaxies could encounter neighbor galaxies by gravitational attraction. And when galaxies merge, remember the distances between individual stars is very large. So stars don't actually collide, but what it can do is to perturb the gravitational potential and have stars redistribute their orbits. And you can see that galaxies are starting to become more round, because when you have these galaxies that are coming in all sorts of directions, it decreases the angular momentum, and that helps to randomize stellar orbits within individual galaxies. And so you see more things falling in. And interestingly, you also see that galaxies seem to fall in filaments. And so at the larger structure, we think of the universe as being isotropic. But what I'm trying to say is that even though galaxies can be found in clusters, it is in fact more like what we call a cosmic web. So it's a bit like a spider's web, where you have filaments that are coming in, and then you have empty regions that we call voids in between them. So galaxies could be coming in from different filaments towards the center. And here we are looking at the simulation of a formation of a massive elliptical galaxy, where, if you remember at the beginning, galaxies were more disk-like and blue and star forming. And once you give it tens of billion years and they have time to merge with all the smaller satellites around it, they become red and elliptical. And now there's only very small satellites around it. And if you give it enough time, those would also eventually fall in as well. So all of this is made with our knowledge of cosmology, which sets the initial condition for the universe and galaxy formation. And then we put in also physics as to, how do we heat up the gas, and how does the gas cool enough in order to form stars? And this is kind of the state of the art, how well we understand galaxy formation numerically. So here is another example. You may have heard of this nice looking galaxy called the Cartwheel Galaxy. Here is another simulation where people try to put in the right physics in order to try to understand, what is what is the formation mechanism of this blue ring around the galaxy. So in fact, the Cartwheel Galaxy is thought to be the result of a galaxy merger. You have a smaller galaxy that is plunging in to a bigger galaxy, and as a result of this collision, there's a expanding star formation ring that is being, well, creating this box. And by looking at the radius and also the location of this box, one could date back the age of this galaxy collision that happened a few billion years ago. And so in my thesis, I actually study interacting and merging galaxies, and yeah, those were, it looks a bit old school now, but we are finding a lot more with James Webb Space Telescope, and they're fascinating for different reasons. And here is another nice reconstruction of what we think galaxy collisions look like. So we are flipping back and forth between actual observations and simulations here. So this is an actual observation of two merging galaxies. And what you can see in this simulation is that when you have two galaxies that are originally disk that are coming at an angle, that is how you can create this irregular structure, sometimes tidal streams or tidal tails. And when galaxies merge together, it is easy to feel star formation, what we call starbursts in the centers of galaxies, because of the torques. They can bring in gas very effectively to centers of galaxies. And at the later stage of these mergers, you will see tidal tails. So those are ways to get rid of angular momentum in order for the centers to merge as well. And so you would find examples of this. And of course, when you look with your naked eye, we don't really see these features, but in a space telescope, that is something that we can see. And sometimes people, what we do when we do classification is that we look at a galaxy that has this shape, and we already know that it is in a late stage merger. And people then can build catalogs of this early stage or late stage merger to compare the properties to understand, what is the effect of galaxy mergers on the star formation of galaxies. And some of you were asking about elliptical galaxies. Indeed, the idea of how elliptical galaxies form is that we think they come from past galaxy collisions. The reason being that we think that galaxies, they were all born as disk galaxies because you have orderly rotation. The process is not too different from how solar systems form. Basically, you would have a flat pancake structure of material that is orbiting, and then they start clumping up, right? So galaxies are like that too. And then for elliptical galaxies, it is a bit of a mystery. How do you make something that is so round, right? And some clues have come from deep observations that make use of smaller telescopes. So here are two examples of elliptical galaxies of shallow images. So shallow being not long exposures, right? When you look at them, you do a lot more stacks and do deeper observations. You can review what we call low surface brightness features, and you don't have to go to space to do that. You can do that with small telescopes as well on a good site. You see these features that resemble, what you saw in the movie, right? Like this rings or spears around them. And those are, here you can even see tails. So those are features that persist for 4 or 5 billions of years after galaxies merge. And from the directions of these streams, you can even reconstruct the previous orbit, to understand where it came from, what kind of galaxy is the companion, and so on. So those are cool things that I think is hard to appreciate, because one could look at an elliptical galaxy and think that, well, it looks boring. I prefer to look at a spiral, but actually maybe we just have not looked deep enough. When you look deep enough, there's always something interesting, and that tells us how they form as well. So back to our home, about the Milky Way. I'm sure you know already, but actually the Milky Way is also set for an encounter to our neighbor galaxy, the Andromeda. And so M31 is expected to merge with the Milky Way in 4 billion years. And so, we are not going to be able to see what happens, but people have made illustrations to see, what will we see on the night sky when that happens. So this is a time sequence. You will see M31 coming closer and closer. So we're starting to look bigger in the sky like that. And then when the Milky Way and Andromeda starts interacting, you have this starburst events where, well, it gets messy on the sky. A lot of new stars will get created because of the gas being compactified and forming new stars. And then we will look like a train wreck for a little while. And then when you wait long enough, then you will find a boring elliptical galaxy on our night sky. So I think if you wait a few billion years, this is what we will see on the night sky. And I find it very interesting to think about. And people would nickname this final galaxy the Milky-Andromeda, which is a combination of Milky Way and Andromeda. And I talked a bit about black hole. This is also one area that we study, well, not just because black holes sound cool, but actually black holes are very cool and for different reasons. So here is an example of Centaurus A. It is another massive galaxy that has an active supermassive black hole. And this is why I also think it is so nice to be able to get information from different wavelengths. So this is a composite image made of X-ray image, radio image, and optical image. So when you look at the optical image of Centaurus A, it looks like an elliptical with a dust lane. But actually, you can see different processes when you look at the radio. The jets become a lot more obvious, that is in purple, and then also in X-ray, right? So these jets, as I mentioned before, they come from the accretion of the supermassive black hole. When you see jets like that, that means the black hole is accreting at a fast rate and growing fast and putting on mass. And a lot of interesting physics happen in there. And I want to highlight this also, that even though black holes themselves are so tiny and compact, it is one of the most energetic events in the universe. And in fact, you only need a few % of this accretion energy of the black hole in order to unwind the whole galaxy. So we study this, what we call feedback process, because it is such an energetic event that we want to understand when you have an active black hole, how does it influence the star formation processes in the host galaxy? Does it? So the idea is that this is energetic plasma being injected into the interstellar medium. It is able to heat gas up or expel gas to thousands of kilometers per second away from the galaxy. So it has the potential to remove all the fuel and gas from the galaxy so that it can no longer form stars. So this supermassive black hole accretion event is important to study for this reason. And I want to say a bit about why we need to put telescopes into space. So human eye is only sensitive to light in the optical wavelengths, and this is where the atmosphere is, well, mostly transparent. But the case is different when you go to higher energies, like when you want to look at gamma ray or X-ray or ultraviolet. The atmosphere is opaque, which is good for us humans because we don't want those energetic light onto us; it would kill us. But that in order to look at those wavelengths, we need space missions, and similarly for parts of the infrared spectrum and also for the radio, the atmosphere is opaque. So there are certain wavelengths where we really need to put telescopes into space, not just for sharper images, but actually the atmosphere blocks and scatters a lot of the light. And what am I trying to say here? I don't know what your opinion on this mega satellite constellations are, but I'm sure when you take deep sky images, you would see the trails. I know some people get very excited to look at Starlink satellites, and if you're an astronomer, then you get concerned because you replay this movie again. This is quite old movie by now, a few years ago. It is at the professional telescope at CTIO, and you can see, you have all these bright satellite trails that are visible even with our human eye. And when you do long stacks, and typically in galaxies, we need to do long integrations. Like sometimes I would stare at one galaxy for the whole night, right? So when we do deep stacks, you see these trails. So of course, in the grand scheme of things, it is something that can be done in post-processing, but the astronomy community is getting increasingly concerned about the effect of this satellite mega constellations. And the reason is also that these are new projects that are getting expanded more and more. So by now, there are thousands of these satellites in the sky now. And I think the goal is to get to tens of thousands of the satellites soon. So I think our night sky would be quite crowded. And I think we're concerned, how is it going to affect our observations? So there's this research paper that have been published by some colleagues here in Canada. And I just want to highlight, so they have studied the effect of this satellite mega constellations. And I highlight this sentence, and I'm going to read it to you. For latitudes near 50 degrees north and south, SATCOM satellites make up a few percent of all visible point sources all night long near the summer solstice, as well as near sunrise and sunsets on the equinoxes. So what that means is that around our latitude where we live here, if we go look in the night sky, actually these artificial satellites make up a lot of the point sources that we see, and they're bright enough that we can see them with our naked eye. And I want to highlight that also that it affects not only optical astronomy, but actually it also affects radio astronomy. And the reason being, the idea of the satellites is also for radio and Wi-Fi communication, right? So of course they would emit in Wi-Fi, in radio wavelengths, and that also affects our radio observations as well. So the International Astronomical Union have been leading different efforts in order to advocate for the need, well, not to not send satellites, but this whole field of, who gets to launch satellites to space is not regulated. They don't need to be responsible for it. So at least we should be consulted. And I think this is maybe what concerns you as well. If you want our night skies to be dark, then yeah, we need to care about what other people are doing, because they clearly don't think about, well, consequences, or maybe they don't care, but we need to express what we need. So here are some extra reports if you want to understand better how it influences different aspects of astronomy. And yeah, you can look up those reports, and I find that quite interesting. Then I want to switch gears a little bit to talk about new space mission. And I showed this on the front slide, but last year on Canada Day, there was a new space mission that was launched, and this mission is called Euclid. And actually it is ESA, so European Space Agency-led mission, but quite a few Canadian astronomers are involved. So on launch day, even though it was holiday, well, some of us here at UBC, we held a launch party in order to watch the launch of the Euclid mission live. And this is a picture of the mission control in Darmstadt in Germany. And so I want to talk about Euclid also because it had been around since a long time, and I want to use it to highlight just how difficult and how long it takes in order for space missions to happen. So when I was still a PhD student, there was a Euclid Mission conference, and I went. I was not super involved because at that point it felt like, well, it's going to happen in more than 10 years. So I don't know where I'll be, right? But I'm somewhere in here. And because the meeting happened where I was studying in Copenhagen. And then, well, more than 10 years later, I'm still in astronomy. I have a career in there. And I went back to Copenhagen for this Euclid meeting because there was just a meeting before launch. And so what I want to emphasize is that the Euclid mission is made of thousands of scientists and engineers from around the world, mostly based in Europe. And they have been developing and designing and optimizing the design of the instrument, doing testing. And then, this launch that happened last year on Canada Day is really decades of effort put into this space mission. And so it involved more than 1,600 scientists from more than 300 institutes in 17 countries on 3 continents, and Canada, or Canadian astronomers, is a small part of it. And the reason being, it is complex and expensive to have space missions, but also that there's a lot that can be done that, thousands of scientists could be doing exciting science with what is to come. So what is Euclid going to do? So Euclid is going to observe 1/3 of the night sky. So this is showing the skies or the areas over the sky where Euclid will survey. And you will see that it avoids the galactic plane, and it also avoids the ecliptic plane because that's where you have a lot more light pollution. But it is going to be a comprehensive optical and near-infrared survey over 1/3 of the night sky. And what is it going to tell us? is going to tell us a lot of things, but it is going to produce a gigantic catalog of billions of stars and galaxies at resolution similar to that by the Hubble Space Telescope. So now Hubble telescope in comparison is a bit like looking through a telescope or binocular. You're just looking through, small pencil beams areas over the sky. Euclid is going to give us access to 1/3 of the sky. We're going to discover so much. I'm a galaxy person, so I'm interested to understand, what in particular we are able to build, be able to characterize the large-scale environment of galaxies to be able to understand if these galaxies are residing in clusters or groups or in voids. Those are things that we can do easily with Euclid. And then for the people who study cosmology, they will be able to use this Euclid catalog in order to investigate the nature of what drives the expansions of the universe, the nature of dark energy and dark matter. I'm going to skip this, but just to give you a taste, because it's been taking spectacular images. This is one of the Euclid's first images that is being released. This is the Perseus galaxy cluster. And you see, this is pretty much like the Hubble space image I show you. And you see, well, the bigger galaxies are part of the Perseus galaxy cluster. But then in the background, you also see a lot of small dots, and each of them is a galaxy. So there's really a lot that we can do. And I talked a lot about galaxy cluster, but I just want to make it very obvious why it is interesting. So when you have a galaxy, the most massive galaxy of the galaxy cluster, they typically have AGN, or active galactic nuclei jets, that is coming from the feeding black hole. And these jets are so powerful that it can actually penetrate all the way into to this so-called intra-cluster medium, which is very hot, 1 million degrees gas that is in the space that is in between individual galaxies in the galaxy cluster. So galaxy clusters, they always have this hot plasma in between them. And in fact, we think that the supermassive black hole in the center is powerful enough, and it goes far enough in order to stir up this gas. So sometimes when we look at X-ray observations, we see cavities in the X-ray, and that is actually due to the influence of the central black hole. And yeah, there's a lot that we can study by cross-correlating optical starlight that you see in Euclid or Hubble with X-ray missions in order to understand the physics involved. And here is another reason why I think it's interesting to look at galaxies that are found in galaxy clusters. This is a simulation of a phenomenon called ramp pressure stripping. So this is what we expect galaxies to look like as they travel through this hot plasma in a galaxy cluster that I talked about. So they're called sometimes jellyfish galaxies, because what you're actually seeing is that stars in gas are being lifted off. Let me replace this. They are being lifted off the galaxy, and the galaxy itself, as it travels through this hot wind of 1 million degrees. So it's like having a blow dryer blowing on it. And we do have evidence of these different jellyfish galaxies that we found in deep space imaging. And that is a way, when we look at the structure, that is a way for us to infer the presence of this hot gas. And also, yeah, we can better understand the gas and star densities of galaxies in a cluster. So I talked about my students. Here are two of my PhD students. And in fact, they have their thesis projects on this precise topic. One of my PhD students, Galaxies, she studies how galaxies star formation varies depending on where they are. Are they in groups or clusters or in voids? And why is that they're different? And another PhD student, Joey Bengal, his PhD thesis is to look for the first progenitors of galaxy clusters in the early universe before they are actual clusters. So we call them protoclusters. So we're planning to use the Euclid surveys to hunt for this the first stages of galaxy clusters and to study their properties. Okay, then the very last thing that I want to mention is that, well, I think we are very lucky here at UBC because we recently installed a new telescope and we commissioned a new telescope in a site called Deep Sky Chile. So it is a telescope that we can operate remotely from UBC or from anywhere, in fact. And that's a small half-meter optical telescope. And we've been using it. I just finished teaching a course to graduating undergrads at UBC, and they had to do projects. Basically, my students had to come up with things they want to observe and also to do scientific observations. So my students were looking for exoplanet transits, or they were looking at different galaxies to measure the sizes and so on. So I taught this lab course, and everybody had great fun operating this telescope in Chile. And these are some of the images of the Crab Nebula and the Running Man Nebula that some of my students took. And here is another animation of the actual James Webb Space Telescope. You can see it. So it looks like a star, but yeah, it is actually the JWST that we can see from those images. And I thought that was very cool that we get to use this small telescope for our teaching. So I think I would wrap up here. I think there's a lot that we can learn about the universe. And in particular, I find galaxies very interesting because they're so complex. And I think we're all here because we want to learn more. So I thank you for listening, and I welcome your questions.
I have a question
Okay.
on the jets. They walk a very long distance. And what impresses me is that they're straight, but the body itself would be rotating. So why aren't the jets curved?
Yeah, that is such a great question. Actually, it is not depicted here. Maybe, yeah, I would stay here. Actually, there are observations where sometimes the jets can be bent, after they come out like that. And this is interesting because we don't quite understand why that is, but we think that the jet orientation really has to do with the orientation of the accretion disk around the supermassive black hole. So the jets come out in perpendicular directions, and sometimes the accretion disk of the supermassive black hole can be misoriented if you have a galactic disk. It does not have to be on the same plane. And in fact, orientation of the accretion disk really mostly depends on the material that is falling in at a given time. So things come in all directions. So the accretion disk of the supermassive black hole gets reoriented quickly on quick timescales. But then on larger scales, we see bent jets, and we think it is because these jets are made of relativistic plasma. And when they start interacting with the intracluster medium, like if they meet a dense gas pocket here, sometimes, they would just get bent like that. So we look for signatures like that, and we then try to get observations of also the intracluster medium to understand how the jet is interacting with the gas within and outside the galaxies.
Could it be that the black hole is actually rotating?
Well, black holes are certainly rotating.
Is actually rotating is a delay in its rotation. So it's rotating, and the jet that's shooting up first is the one that's getting bent over, right? So it's turning. The jet shoots up, black hole turns, and then it ends in its rotation.
Yeah, I think they have two frames
Is that
here.
true spectra there?
Is not. I think black holes in general do rotate. They do have spins. The thing is that jets, they generally come from the accretion disk around the supermassive black hole. So the way I think about spin is that the spin of a black hole is kind of like, it has a memory of all the angular momentum of the stuff that fell in the past, right? So it is not, the spin does not always align simultaneously with the accretion disk. If that makes sense. It is like an integral of, all the directions of the materials falling into the black hole. But the jets themselves, they are mostly perpendicular to the accretion disk itself, which then depends on what kind of orbits are those gas on, whether the accretion disk, normally it is not a thin disk, it is a puffy disk, and we don't really know its structure because we can't really image it well, but we think of it as having somewhat like a donut shape, and things are on kind of chaotic orbit. So things can fall into the central black hole from different directions at any given moment.
One question.
I was reading some stuff online about a month ago to do with research that's being done on mapping the magnetic fields in galaxies. And it struck me that, whoa, this is looking complicated because you've got magnetic fields, like the magnetic field of the sun is just, it's a nightmare, a Gordian knot. And the galaxies, as portrayed in this article, the magnetic fields in and around them looked every bit as complicated.
Yes.
Now, theoretically, if you got a black hole in there that's booting out material, plasma, which is charged particles, it will interact with magnetic fields.
Definitely.
Right? Okay.
Well, not just interact, but I think I didn't make this point super clear, but I want to say that these jets are actually collimated precisely because of the magnetic field the accretion disk around supermassive black hole, as I mentioned, it is 1 million Kelvin or 1 million degrees Celsius gas, right? So these are already hot plasma that is, rotating, and that generates magnetic field that kind of confine the plasma jets to be very collimated. So you're right, when these jets, and they themselves, they are on kind of helical orbits, right? So they themselves, when they go out, they also could be generating magnetic fields. You're right. So I think the jet is one of them. And then one would have to think about what other plasma are in galaxies. If a galaxy is rotating, or if there are other kinds of outflows, for example, or there could be massive stars, like neutron stars, for example. They are very small, but I think if you have a bunch of them, then that could, mess up the magnetic field lines as well. So yeah, it is messy.
I'm wondering how many people here do galaxies in.
Quite a few. There can be more. There's a lot to be done. So how did you hear about it? Oh, God.
I don't remember.
It's like 30 years or 20 years.
Well, it's been since 2007.
Yeah, it's been a while.
And now it's Zooniverse, which is a whole lot of projects that are doing all kinds of things. But yeah, it was the Sloan survey. And they realized they had so many galaxies, they didn't know how they were ever going to get through them all. And someone said, what would happen if we did a picture and some instruction? And the next thing you know, people all over the world are jumping at. So yeah, it's a great example of citizen science.
Yes.
And if it's a cloudy night, you got better to do. You're an astronomer, hey, galaxies are.
And I like it that it is designed a bit like a game. It's not like you have to commit hours to it. You just do it when you have time, right?
And if you see a picture you really like, you put it in your album.
Yes.
For the black hole, you have an image of a black hole. You have a rough concept of where the black hole is.
Yes.
As you go toward the center of the black hole, the very center of the black hole, does the gravitational field of the magnetic field and the mass all increase proportionally as you move toward the center of the black hole and the heat?
I think this is a tough question because within the event horizon, I think those things don't really matter, or let's say we don't have answers for, because we don't really understand the internal structure of a black hole. And that is where classical physics fail. And we know that we need, general relativity, but even so, I don't think we really understand the internal structure of the black hole. So the event horizon that we see is, it comes from, we see them, but there are also many magnetohydrodynamical simulations of what we think plasma look like as they approach the event horizon, and interesting relativistic phenomena that happen there. But if you're talking about the accretion disk, then yes, the temperature increases as you get closer to the black hole, because things are spinning faster.
We could infer that the black hole might have similar properties, even though we can't verify it at this time.
properties as in the spin?
Well, that all these elements, as you get closer and closer to the center of the black hole, each of these properties will actually increase proportionally to one another until you get to the very center. We can't, by your description, we can't know that, but we can know it from the edges.
Yeah.
And as we go toward from way out toward the edge of our horizon, and then enter into the black hole itself, where we can't get the data.
So I think
Consistently, to have consistency, this gravitational field, the magnetic field, and the mass density, the mass density itself should all increase until you get to the closer you get to the center. It would seem to fit within the physics of the creation of the black hole, or of the Big Bang, right, where everything was condensed into a little tiny little ball, and then it exploded. But that would kind of contradict the Big Bang theory. We have all these jets which are blowing away energy, kind of like a pressure cooker that's blowing off steam. How would the Big Bang have actually taken place? But I'm digressing.
yeah, I
When
think
you use the word plasma, do you
Yes.
use it descriptively or as a physics term?
it's a
as
physics
state of
term.
matter?
Plasma means hot and ionized gas to me.
Okay,
Yes.
so it's a state of matter.
Yes. To answer your question, I think it is a bit paradoxical to think, but a black hole is at the same time complex and simple. In order to describe a black hole, you really only need two parameters: its mass and its spin. So really what I'm trying to say is that, yes, we don't really understand the stuff that happens, what a black hole structure is like. We don't understand the density distribution within a black hole. Like outside the event horizon, we approximate the black hole as a point mass. It's like a singularity, right? So the stuff that you mentioned about, how the event horizon image looks like, it is all about the plasma around it. It does not matter in the simulation sense, other than the mass and the spin of the black hole. It is all just the complication comes from the plasma around it, how fast they are spinning around, and what is the geometry of this donut that is spinning around. And also then you put in relativistic effects so that you can visualize how this event horizon would look like from a certain viewing angle. But in those simulations, the black hole is simple. It is just the mass and the spin.
And charge.
Yes, thank you.